Think about how often we instinctively rank things. You know, comparing sports teams, deciding which snack we prefer. Often it just comes down to these one-on-one choices.
Absolutely. It's a fundamental way we process comparisons.
Okay, so let's unpack this. Today, we're diving into a really interesting mathematical model designed specifically for that, analyzing these pairwise comparisons. It's called the Bradley-Terry model.
That's right. It's a very neat piece of applied mathematics, and its reach is, well, quite surprising.
So what's the core idea? How does it work?
Well, at its heart, the Bradley-Terry model gives us a way to estimate the probability, really, the likelihood that one item, let's say item I, will be preferred over another, item J.
Okay, preferred or chosen, or maybe beats it in a sports context.
Exactly. Preferred, chosen, beats it. It depends on the context. But the model links this probability to underlying scores or strengths that we assign to each item.
Scores, like a rating.
Precisely. Let's say item I has a score, we can call it pi, and item J has pj. The model proposes a simple formula for the probability that I wins against J.
And that formula is?
It's just the score of I divided by the sum of the scores of I and J. So pi ij, pi plus pj.
Okay. So if pi is much bigger than pj, that probability gets close to 1.
Exactly. A higher score means a higher chance of winning the comparison. It's quite intuitive, really. It translates those relative strengths into outcome probabilities.
What's elegant, as you said, is how this relatively simple idea connects so many different fields.
It really does. It's quite remarkable.
You mentioned diverse fields. I immediately think sports rankings, naturally.
Yes, definitely sports. Ranking teams in basketball, players in chess, that's a classic application.
But where else does it pop up?
Oh, lots of places. Think about market research or consumer science. You want to know what chocolate people prefer? Or which wine?
You could give them pairs to compare.
Precisely. Paired comparison surveys. The Bradley-Terry model takes that data, preferred chocolate X over chocolate Y, and estimates an underlying preference score for each chocolate.
Interesting. So beyond snacks.
Definitely. It's used in analyzing social dynamics, like dominance hierarchies in animal behavior studies.
Who pecks whom in a group of chickens, that sort of thing.
Kind of, yeah. And in more technical areas, too. Ranking academic journals based on citations or prestige, ranking different AI models based on performance benchmarks.
AI models, wow.
Yes, and even figuring out document relevance in search engines. Sometimes pairwise judgments are used to train those systems. There's also a system called GADL used for judging, which relies heavily on this model.
So from chickens to AI, that's quite the range. Okay, let's talk history for a moment. Bradley and Terry, 1952.
That's right. Ralph Bradley and Milton Terry published it then. Though, interestingly, the core mathematical idea was actually studied earlier by Ernst Zermelo.
The Zermelo, the set theory guy.
The very same. He looked into similar problems related to chess rankings back in the 1920s, but Bradley and Terry really formalized this model.
Got it. Now, you mentioned the formula, PRIJ, pi plus pj, but I saw another form involving exponentials.
Ah, yes. That's the form Bradley and Terry actually used in their paper. They set the score pi equal to e, raised to the power of another parameter. Let's call it beta ti. So pi e.
Okay, why the extra step?
It gives the formula some nice properties. The probability then becomes ee plus e. If you then take the logit transformation of this probability.
The log odds, right, log p1p.
Exactly. The logit of paj just simplifies very neatly to payday.
So the log odds of winning is just the difference in these underlying beta parameters.
Precisely. It directly represents the difference in strength on a logarithmic scale. This form also highlights a connection to logistic regression.
How so? Logistic regression predicts probabilities based on features, doesn't it?
It does. It's a similar mathematical structure, but used differently here. In logistic regression, you usually know the features, like the beta values, and predict the probability. With Bradley-Terry, we usually observe the outcomes, who won, and we want to infer the underlying strengths, the beta values.
Ah, okay. Different direction of inference.
Right. And just as a side note, this exponential form is mathematically equivalent to the ELO rating system used in chess, just with a different scaling factor. ELO uses a base of 10 and a scale factor, often 400.
Interesting connection. So these models handle pairs well. What if you need to rank, say, 5 items all at once based on some preference data? Does Bradley-Terry extend?
Not directly, but there's a closely related model that does, the Plackett-Luce model. Think of it as the generalization of Bradley-Terry for ranking more than 2 items.
So it gives you the probability of a full ranking, like item A, C, B, D.
Exactly. It assigns a probability to every possible permutation or ranking of the items.
That sounds potentially complicated. Is there an intuitive way to grasp it?
There is. One good analogy is the urn model. Imagine you have an urn with colored balls, where the number of balls of each color corresponds to the item's strength score, its p-value.
Yeah.
To get the top-ranked item, you randomly draw one ball. The probability of drawing a specific color depends on its proportion among all balls. Let's say you draw a red ball first. Red is ranked #1.
Then you draw again.
You draw again, but without replacing the red ball. Now, the proportions have changed slightly. You draw the second ball, say it's blue. Blue is ranked #2. You continue this until all balls are drawn, giving you full ranking. The Plackett-Luce model calculates the probability of getting that specific sequence.
That helps visualize it. So the probability changes at each step.
It does. Another way to think about it is the exponential race. Each item I is like a runner whose speed is proportional to its score pi. They all start a race at the same time. The first one to cross the finish line is ranked highest, the second is ranked second, and so on. You can mathematically sample rankings this way.
Neat. And how does this relate back to Bradley-Terry?
The Bradley-Terry model is actually a special case of Plackett-Luce. If you only consider rankings of two items, pairwise comparisons, the Plackett-Luce formula simplifies exactly to the Bradley-Terry formula.
Ah, consistency. Okay, so we have these models. But in practice, we usually start with the data, right?
Yes.
The results of comparisons, who beat whom, which product was chosen. How do we get the scores, the pi or LA values from that data?
Right. That's the most common task.
Yeah.
Inference. We need to estimate those scores. The standard method is maximum likelihood estimation, or MLE.
MLE, finding the parameters that best explain the data we saw.
Exactly. You write down a function, the likelihood function, which essentially says, given a particular set of scores, P1, P2, Pm, what's the probability of observing the exact win-loss outcomes that we actually recorded?
And we want to maximize that probability.
Precisely. We find the set of p-values that makes our observed data look most likely, according to the model. We often work with the logarithm of likelihood, the log likelihood, because it's mathematically easier.
Is there a formula to just calculate these best scores directly?
Unfortunately, no. There's no simple closed-form solution. However, Zermelo actually proved way back that this log likelihood function has a unique maximum. So there's a single best set of scores.
But we can't just calculate it.
We have to find it iteratively. We start with some initial guess for the scores. Maybe all scores are equal to 1, for instance.
Okay, like a baseline.
Yes. Then we use an update rule, derived from the mathematics of the likelihood function, to refine those scores based on the observed win-loss data. We repeat this update process over and over.
Until the scores stop changing much.
Exactly. Until they converge. The scores gradually adjust until they settle on the values that maximize the likelihood.
I saw a couple of different iterative formulas mentioned. Any practical difference?
There are a few variations.
Yeah.
One comes directly from setting the derivatives of the log likelihood to 0, but there's another one that often converges faster in practice.
What does that faster one look like, roughly?
Roughly speaking, it updates a team score, say pi, based on a ratio. The numerator involves the sum of scores of teams it beat, weighted appropriately. The denominator involves the sum of scores of teams it lost to, again weighted. It's a bit more complex than that, but that's the gist.
And there's a normalization step.
Yes, that's important. After each iteration of updating the scores, we usually normalize them. A common way is to divide all scores by their geometric mean.
Why normalize?
It keeps the scores on a consistent scale. Without it, the scores could all drift upwards or downwards together in each iteration, making convergence harder to track. Normalization anchors them, usually so they multiply to 1 or sum to a constant log score value.
The example with the 4 teams, A, B, C, D, really helped clarify that. You start with 1, 1, 1, 1, apply the update formula using the win counts.
Right. You calculate a new score for A based on who it beat and lost to, weighted by the current scores, initially all 1. Do the same for B, C, and D.
And then you normalize those new scores. The example showed the first iteration leading to something like 0.5, 1.4, 0.7, 2.0 after normalization.
Approximately, yes. Those were the normalized scores, 0.516, 1.413, 0.672, 2.041 in the example. Team D did well, Team A not so much in the first round adjustment.
And you just keep repeating that process, update, normalize,
until the scores stabilize. The final converged scores then represent the estimated relative strengths. In that example, D ends up strongest, B second, and A and C quite close.
Makes sense. Are there variations on this basic model for specific situations? I saw something called crowd BT.
Ah, yes. CrowdBT is an interesting extension designed specifically for crowdsourced data. Think about getting preference judgments from lots of people online.
Like on Amazon Mechanical Turk or something.
Exactly. The issue there is that not all your judges or raters might be equally reliable. Some might be guessing, some might be spammers, some just aren't paying attention.
So CrowdBT tries to account for that.
It does. It tries to simultaneously estimate the item scores, like the standard Bradley-Terry model, and estimate the reliability or quality of each individual judge providing the comparisons.
Clever. So it can downweight judgments from unreliable sources.
Essentially, yes. It aims to get a more robust estimate of the true item scores by filtering out noise from unreliable judges. It's been used for things like ranking document reading difficulty based on crowdsourced comparisons. It helps identify those potentially problematic raters.
That's very practical. Now, there was also mention of a BTL model in software called Conquest.
Right. BTL stands for Bradley-Terry-Luce. It's basically the same model, often framed within that logistic pairwise comparison context we talked about earlier with the Briner parameters.
And Conquest.
ACE or Conquest is a statistical software package that implements the BTL model, among others. It lets you easily fit the model to real data.
The example used Australian Football League results.
Yes. They took game results, who played whom and who won for 16 AFL teams over, I think, more than 2,000 games.
How do you feed that into Conquest?
The input is typically simple. Just lines saying Team I, Team J, outcome, like Team A beat Team B. Then you write a small command file telling Conquest what model to use, pairwise comparison, what the data format is, and what output you want.
And what kind of output do you get?
You get the estimated strength parameters, the affine values for each team, usually on a logit scale. Importantly, you also get standard errors for these estimates.
Standard errors tell you the uncertainty.
Exactly. How precise is our estimate of Team A's strength? The software often constrains the parameters, maybe forcing the average bay to be 0 to make them identifiable. The AFL example showed the resulting table of team strengths, highlighting Geelong as strongest and Richmond as weakest in that dataset.
Does it tell you how well the model fits?
Yes, it provides residuals. These measure the difference between the actual outcome of each game, did Team A win or lose, and the probability of that outcome predicted by the fitted model. Large residuals might indicate games where the outcome was surprising, given the estimated team strengths.
And there was a visual tool mentioned, a right map.
Yes, the right map is very useful. It plots all the estimated team strengths, the map parameters, along a single vertical scale. It gives you a really clear visual overview of the hierarchy. You can easily see who's strong, who's weak, and the relative gaps between them.
So Conquest packages the BTL model nicely for analysis. What about going beyond simple win-loss outcomes? Are there even more general versions?
There are. People talk about generalized Bradley-Terry models, or GBT models. These are designed for situations where the comparison outcome isn't just binary.
Like what?
Maybe the outcome is the margin of victory in a game, which is a discrete value. Or perhaps it's some continuous measurement comparing two things. GBT models extend the framework to handle these richer types of pairwise comparison data.
Do they have good mathematical properties?
Often, yes. Under certain conditions, particularly when you incorporate some prior beliefs about the scores using Bayesian methods, like assuming scores follow a Gaussian distribution, the function you're trying optimize, the negative log likelihood or posterior probability, has a property called strict convexity.
And why is convexity good?
It guarantees that there's one single, unique, best solution for the scores, and it means that computational algorithms to find that solution are typically stable and efficient. These GBT models also tend to have other nice theoretical properties, like monotonicity.
Meaning if A consistently beats B more often or by larger margins, A's score will definitely be higher.
Right. And also a kind of resilience. Adding a few new comparison results usually doesn't cause wild swings in all the existing scores. The estimates update smoothly.
So more flexibility, more complex data, but still mathematically well-behaved. The notes also touched on using Bradley-Terry for statistical inference, like with NBA rankings.
Yes, you can embed the model within a more formal statistical inference framework. Think of each NBA game outcome as a random variable, say a Bernoulli trial, win-loss for the home team.
Okay.
You can model the probability of the home team winning using not just the difference in team strengths, but also adding a parameter for home court advantage, let's call it.
So the log odds of winning would be like ALA plus home BI.
Exactly.
Yeah.
That log odds formulation is common.
Uh,
Log Pelnesi down Pelnesi. Now, you have these parameters, all in and all the use foom. But there's an issue.
Over-parameterization. Too many knobs to turn.
Precisely. You can add a constant to I and subtract it from all the i's, and the probabilities stay the same. So you need a constraint. A common one is to just fix the strength of one team, say Mollier's equals 0 as a reference point.
Okay, that anchors it. Then how do you estimate I and the other books?
Again, typically using maximum likelihood estimation. You write the likelihood function for all the observed game outcomes given, and the bows. Take the logarithm and find the parameter values that maximize it, usually by setting partial derivatives to 0 and solving numerically.
Can you test hypotheses with this? Like, is there really a home court advantage?
Absolutely. You can use statistical tests like the generalized likelihood ratio test, GLRT. You'd compare the likelihood of the full model with I, the likelihood of a simpler model where you force I to be 0. If the full model fits significantly better, you conclude that I is statistically significant. There's evidence for a home court advantage.
And can you get confidence intervals? Like, how confident are we about the strength difference between the Lakers and the Celtics?
Yes. The MLE theory tells us that the estimated parameters, hats, are approximately normally distributed, especially with lots of data. The variance and covariance of these estimates can be found from the second derivatives of the log likelihood function, essentially, the inverse of the Hessian matrix, also known as the Fisher information matrix.
Okay, that's getting a bit technical.
It is. But the upshot is you can use that information to calculate confidence intervals for individual parameters, like I's, or for differences between parameters, like Pickel's Celtics. This gives you a range of plausible values for that strength difference, quantifying the uncertainty in your ranking.
Wow. So starting from just pi+pj, this whole framework blossoms into quite sophisticated statistical modeling.
It really does. It goes from a simple, intuitive idea for pairwise comparison probabilities to a powerful toolkit for ranking, understanding preferences, modeling complex outcomes, and performing rigorous statistical inference.
It's fascinating. So to sum up, the Bradley-Terry model gives us this core way to analyze pairwise comparisons by assigning underlying scores or strengths.
Right. And the probability of one beating another depends directly on those scores.
It has incredibly broad applications: sports, consumer choice, animal behavior, AI, search.
And it generalizes to full rankings via the Plackett-Luce model.
We estimate the schools typically using maximum likelihood estimation, often with iterative algorithms.
And there are extensions like CrowdBT for noisy data, software like Conquest to make it easier, and generalized BT models for richer comparison outcomes.
Plus, it integrates fully into statistical inference, allowing hypothesis tests and confidence intervals.
Exactly. It's a really valuable framework for anyone dealing with comparative data. While the basic idea is easy to grasp, the depth you can go into with the extensions and statistical tools is quite profound. It's a beautiful piece of applied mathematics.
This has been incredibly illuminating, a great look at the power behind ranking. Now, for you, the listener, here's something to think about. Consider a situation in your own life, maybe your work, maybe a hobby, where things are constantly being compared, implicitly or explicitly. How might thinking about it through the lens of the Bradley-Terry model, thinking about underlying strengths and pairwise probabilities, offer some new insights? It's definitely a framework worth mulling over.